Welcome to the Ultimate Plastic Welding webinar. We are here to talk about plastic welding. We're going to answer your questions. Those take priority. That's why it's the first bullet point on the topics list. We'll give you an introduction to Extol. We'll talk about the basics of plastic welding. Then we'll compare different types of plastic welding. And then we'll talk about how to decide which technology is best for you and your product. I'm Jason Dornbos. I've been with Extol for 15 years. Presenting with me today,
Catherine Urives. Oh, been with Extol for 8 years? You put me on the spot with the number of years there. We'll go with 8 for now.
And
my name's Nick Flesher. I've been with Extol for 14 years.
Woo! And let's see, hold on. Okay, so during the registration, we asked the question, which welding technologies are you most interested in? And the ranking there is sort of what people said when they registered, but I'm curious to know, people that are on the webinar right now, is there a specific question that you have that you are hoping to have answered today? Yeah. And if so, what is it? Because we certainly will talk about laser welding. We're going to talk about hot plate welding and ultrasonic welding and vibe and spin and infrared and heat staking. So please put your questions in the chat. We're going to answer those as we go along, and we're really hoping that this is very interactive. Think of this almost as an Ask Me Anything webinar. As long as it's plastic welding related, then we'll work to answer it. We're not here to answer philosophy questions or any of those other. No, we're focused on plastic welding. So let us know. What do you think? There are a few of you who have used the chat. If you're looking for the little chat button and you can't find it, maybe you got to click on the little ellipsis that says more and go to chat. And Nick has posted in there and said, if you have a question, type it here. We got 37 people on this call. We should have a question or two, or maybe yes, I really want to learn about laser welding. I don't see anybody typing yet.
No.
They're just really trying to sort through all the good questions that they've got.
You guys there?
Is this thing on?
Well, Jason, if I'm assuming questions will come while we get going.
Fine. So let's do an intro to Extol while everybody's typing, and then hopefully you guys can deliver some more questions, because that'll be great.
Yeah.
So Extol is a manufacturing technology company that helps improve how plastic products are made. We specialize in solving tough challenges for plastic product manufacturers. We believe that the needs of each application are unique, so the best equipment solutions should be tailored to meet those needs. That's why Extol has both plastic welding expertise and custom automation expertise. Our welding skills equip us to solve the toughest plastic welding challenges, and our custom automation expertise enables us to tailor equipment to meet your specific needs. When you work with us, you don't have to choose between plastic welding expertise and custom automation expertise. We don't make you compromise. You get a configurable plastic welding solution that is optimized for performance. If you look at this slide here, you can see a breakdown of all of the different things that you can get from us. Engineering services will help you with developing and testing, and we'll partner with you to figure out what's the right way to produce your plastic parts. We have all these different plastic assembly technologies at our disposal. And then we make equipment too. So we can make you a custom machine or automation. We have standard equipment options, and then we can integrate any of our plastic welding or assembly technologies into a machine that you're building, or that you have a machine builder building for you. Our plastic assembly technology is actually 2 different categories. There's welding technologies. Those are the ones like infraweld, infraguide, laser welding. There's different types of IR, like quartz IR, hot plate welding, spin welding. We're going to talk about all of those. And then the other category is staking technologies. So what are these actually like? What's the difference? When we say plastic welding, we're talking about plastic materials bonding at the molecular level. So these are 2 plastic surfaces coming together. They're going to bond. Plastic staking is a mechanical retention. So one of the components is plastic, but the other component doesn't have to be. And we're just forming a plastic post into a cap that retains that mating component, whether it's a circuit board or a metal bracket or another piece of plastic. or sometimes a thin, flimsy gap hider or something fabric related. All right. So which kind of questions are coming in?
We have 4 or 5 questions.
Really
Great
good
questions.
questions.
All folks needed to know was we were for real, Jason, before they actually started
Yes,
testing.
we want the questions.
So we're going to go in order. Max, you asked about ultrasonics. You have equipment that has some flex issue when compressing. I'm not sure if that's tooling related, lower nest related, horn related, or material related. I would say, first off, Extol integrates ultrasonic equipment. We don't make our own ultrasonic equipment. So if it's horn specific, we typically buy that from the ultrasonic manufacturer of choice. We'll work with all the large companies, and most often our customers specify that. So if it's horn related, that has to be very precisely engineered with proper FEA and make sure that it's tuned correctly. Lower nests, kind of tricky. You actually want a really rigid nest typically for ultrasonic welding. Otherwise, you can generate heat at the surface, which can cause some challenges. So a bit of a general question. I would say flexing in ultrasonic welding, if you have any sort of flexing, that's probably going to be a challenge for weld quality, repeatability, and most importantly, I would say generating heat where you don't want it.
Yeah.
So I would say it's not.
Is your machine's column flexing?
That's what I wonder.
It shouldn't be.
Said it is the flex from the post of the equipment.
Yep. So the
Okay.
column is
That is no good.
that's bad.
Yeah, you can't do that.
So either you need a new machine or you need to, I don't know how much force you're using. Is it
Reinforce it maybe. It might be too much force. You might need different amplitude. Try to bump up your amplitude. Yeah, I don't know. That's pretty specific. I think the best thing to do there would probably be to go to the manufacturer of the ultrasonic welding equipment and see if it's on the ultrasonic side, which sounds like it's more on the integration side, the implementation side of it. We'll have to see where we get with time as far as if folks on the call, ultrasonic is probably the most common welding technology out there.
Yeah.
But we can explain a little bit of what ultrasonic is like if we have time here.
Okay.
I'd be curious to learn about which plastic welding methods are least likely to cause material property degradation like embrittlement.
Okay, that's a good one for us to answer once we've gone through some of these, I think.
Yeah, I would say that's true.
Feasible for PEEK.
PEEK material for laser welding process for medical applications. Absolutely. PEEK in sort of a natural form can be a little bit of a transparent material. So you could use 2 micron potentially. If you're going from a natural PEEK to like a black PEEK, it's very, very simple to laser weld that material. So we'll probably talk a little bit about how we trial materials in our applications lab at some point. But in short, we do sort of complementary material trials, especially for laser welding, because the material properties are really important. But we have an apps lab where we can trial that for you. Really good question.
I would also say that there's lots of different grades of PEEK.
Yeah, I was just going to say, I've actually seen probably 4 or 5 different grades of PEEK in the last 2 weeks alone. And some of them are laser transmissive, which means you can do 1 micron laser welding with it, and some of them are not. So just because it's PEEK under that umbrella, there's a wide variety. So there's an amber colored one that is laser transmissive.
Natural.
And then there's a more bone color that is not laser transmissive. So I think really leveraging, like Nick was saying, the material testing for your specific PEEK. PEI is the same way, where those highly engineered resins do have quite a spectrum of transmissivity. So definitely can take a look at it and dig into your application more.
These questions are phenomenal.
How does the strength of plastic welds compare to the parent material? We can address that as we go through the technologies. Is hot gas welding available? No.
Yeah, there's a company that has a patent on that, and we've actually found that it can be cost prohibitive. You have to generate nitrogen, and you consume a lot of power, a lot of gas. So we haven't really dove into that. Plus, there's kind of one particular company that does it, and they have a patent that we really kind of are steering clear of.
Well, there was a question that was missed about the best way to control overheating with a polypro joint for hot plate welding. So, not sure if you want to talk
I'd love to dive into that quickly. We hot plate weld a lot of polypropylene, and for some applications, strength is really, really critical. For most applications, strength's important, but in some cases, strength is really, really important. And so trying to stay below a 750 degrees Fahrenheit is kind of advised if strength matters a lot. But the hotter you run that hot plate weld process, the less time on the heat plate and the less heat affected zone you have to all the adjacent parts of the part or sections of the part. So that question, I think, is kind of there's a couple of variables, I'll say, in that equation, and one of which is strength. We do a lot of it, though, and we can use temperatures from 650 up to 750 is typically the window. Mm-hmm. And it also depends on how quickly you can get that melt to where you want it to get off of the heat plate. Mm-hmm. So Jason's pulled up the hot plate welding process. If you're new to hot plate welding, it's a very simple, straightforward process where there is a central heat plate. The two plastic parts are on both sides of the heat plate. You make contact with the heat plate. Then you have an open time where the heat plate has to get out of the way. And then our weld process is a very precisely controlled position or force. So you just need, for really all plastic welding, heat and pressure. And the hot plate welding process is that. It's a really good question with polypropylene. We'd love to get specific to the application maybe after the webinar.
Yeah. I think this is going to be my theme today. Similar to what I said about the peak, polypropylene also has a pretty big umbrella as well. There's polypropylene, natural, or there's copolymer polypropylene. And those two react very differently to the heat plate as well.
Yeah.
Some blends of polypropylene require maybe the use of like a Teflon coated tool to get that strength requirement. And then if you're using just straight polypro, you can get away with those higher temperatures.
Actually, so Jeff sort of gives some context there. They are using a copolymer. Copolymers really are also a wide range. We have seen strength of copolymers can be a challenge, as can sticking. We do have some sticking sort of sub-processes. I won't get into the details of those, but microtoming that, if you're not familiar with that term, is an ultra-thin slice, and you can inspect the heat affected zone, the melt zone, and kind of how much material is remaining there, so you're not doing cold welds.
Wish I had a picture.
I know.
I don't have that queued up. Sorry,
Jeff, you're right. I mean, I think brittle joints on those welds might be the copolymer blend. Mm-hmm. We've seen a lot of companies have switched from straight polypropylene to copolymer blends from a cost standpoint, mm-hmm. And that comes at a compromise of strength in some cases.
Yeah.
So I would say, see if you can bump your temperature up and actually reduce the melt time. You probably have already tried lower temps. You probably get sticking at 650 and 600. And Catherine's right. Teflon is not a great solution, but it can increase strength.
The only other question I think that we haven't addressed yet is about tuning ultrasonic horns. And Extol doesn't have the ability to tune ultrasonic horns. We would purchase those from a company, and they would do the tuning.
Yeah, so. And we have done that. We've worked with companies to do that tuning.
Did we answer Steve's question about how the strength of plastic welds compares to parent material?
We're going to. Yep.
It does. In short, it does. Parent material strength is sort of the industry term, and what that essentially means is if you have a given wall thickness and surface area, how much reduction do you get from the welding? If you're not familiar with that term, that's kind of what that means. Really good welds are 90%. You can some companies will sort of cheat a little bit, and if the weld rib is a little larger, they'll say you can get 100% or 110% parent material. That's not accurate if you hear that term, because it's a ratio of surface area, not just force.
Right.
So we'll talk about that because there's various ranges across. Well, let's talk hot plate while we have it up, Jason.
Yep.
What do we typically say? Around 80 to 90%, if I'm not mistaken?
If it's a 1-to-1 wall stock to weld.
Yep.
Yeah.
Yep.
But I think if you do a 2-to-1 ratio of your weld rib to your wall stock, you can parent material.
You can, pretty straightforwardly. Yep. So hot plate, and it also depends on, and this is true for all plastic welding. If you have glass, talc, regrind, which I'm assuming everyone on the call has dabbled in some of those sort of fillers, it can affect your strength. We typically see negatively, especially with hot plate welding, because those glass fibers don't really cross the barrier of the weld joint. So typically it's a reduction. We don't have really good rules of thumb on that, I don't think. Would you say, Jason?
Like a specific production.
Yeah, based on
Okay, yeah.
glass. Yeah,
All you can, it just
we have to test it.
those fillers aren't going to weld, so you're reducing effectively you're reducing the surface area of your weld by a percentage. So,
Right.
Ricardo says he's got a new project for vibration welding, and it's PMMA with a high gloss black, and there's concerns that there's going to be marking on that part from the vibration process. I'm going to pull open so people can follow along. When we say vibration welding, we're talking about the one on the left. That's two materials linearly being vibrated left to right. And it's a pretty aggressive process. You're applying a force and sliding back and forth to get the friction to generate heat. And because it's vibrating, if you aren't holding your plastic part really tightly, the plastic is going to shake in the nest itself, and that's going to scuff the plastic part like crazy.
Not to mention just a teeny tiny little piece of something in your nest.
Oh, yes. Yeah.
Done.
Yep.
Game over. There's
So
nothing you can do.
he's talking about a resonated nest where you have, some softer touch materials in your nesting. Do you know if that's going to be enough to reduce the risk? I think there's always going to be some risk.
There's always risk. What I would say from what we've had experience with customers that use a resin or a poured, a softer material nest, I'll just speak generally, a softer material, is you have to keep it clean. So, you might need work instructions where your operator's hitting that nest with air every single part. We actually have seen customers have to do that.
Mm-hmm.
We've seen, I call it a moleskin material. Vibration welding is pretty aggressive on that. So I'm probably thinking more in terms of like hot plate welding where you don't have that aggressive vibration, but that could be something to try. The biggest thing I've seen companies in your sort of applications is the lens hitting CAD? Are you holding it securely, and is it completely secure in that nest? Because plastic be plastic, and
Maybe plasticking.
it'd be warping, and plastic be plastic. I think hitting those dimensional consistencies will be probably the bigger challenge to making sure you don't get marks where it fits. In the middle of the summer when humidity's high, it's going to fit differently than in maybe wherever you may be in the world when it's cold and the humidity's lower and that part's a little bit smaller. So make sure your nesting fits sort of regardless of what material is what I would say.
Vibration welding is kind of one of the most, vibration and ultrasonics are two of the most known, maybe, welding technologies. I'm curious, Nick, what would be other technology avenues for people who are maybe currently considering for similar lens application?
You've put me on the spot. I think heavily it depends on budget. I mean, anybody who's talking welding, what's your budget? What's your performance criteria? So when you say that, my mind immediately goes to, well, if budget's not a concern, laser welding.
Mm-hmm.
If size is a little bit smaller, laser welding actually can be more close and from a budget standpoint to vibration than what I think a lot of companies think. We've been told that a lot recently as a laser welding provider, that can be a good solution. But if it's a really complex geometry, then you're talking simultaneous laser welding. And so, which is all of that weld rib having laser energy at one time. So that's probably the more gentle of all, but could be the most expensive of all.
Yeah, when you say gentle, you mean because it's just not that abrasive process.
Yeah.
Once the parts are clamped together, there's very, very minimal.
Right. If you can't tell, I'm sitting on the right side and Catherine's sitting on the left side. So if you see us talking to one another, I think we have seen hot plate replace vibration in some cases, but PMMAs, PCs, PC ABSs can string a little bit. So you have to have that process window is quite narrow. So that would be another non-abrasive sort of welding technology, but you did put me right on the spot. I'm here for it.
I was just thinking,
Let's go.
We understand what the risks and benefits are of vibration. What potentially would you otherwise throw in the ring?
Those are
Kind of
the other two I would say.
there, so.
Great question.
At $700, we get oxidized poly that stick to the coated hot plate and then transfer back into the next joint and weaken the joint.
Yeah.
Stronger at lower 560, but
Yeah.
can't manage the stringers.
Is there a hot plate cleaning system? For three-dimensional shapes, unfortunately, the answer is no. We have done Teflon sheets and Teflon tools. That could maybe get you into the 500 degree range, but 560 is probably too high for those coatings in those sheets. I would say if you can get stronger, try it at 800 if your welder can go that high. Our welders go up to 1,000 degrees Fahrenheit. And the whole goal, that might sound counterintuitive, but the reason that's the case is you can run that heat plate on the plastic for a much shorter amount of time, and it should help with your stringers. So I would say try going way hotter than you think. We actually have seen that work, but we've also seen that weaken the weld joint. So depends on your application.
Yeah.
Really, the question is for Jeff, I guess. When you say coated hot plate, can you elaborate on what the coating is?
Yeah.
Because
This This is 800 degrees. See if that helps.
I think that's a white ABS.
Yeah. So what I wanted to point out is it's coming in. It opens right there. I'm pausing the video, but it actually hesitates. The welder's programmed to hesitate right there, and because it's really close to a really hot tool, those stringers get vaporized before pull away. If you've got chromium-based coating, which it sounds like you do, you can go hotter. Yep. So
yeah, the 550 might be too low for the chromium.
Yeah, that's going to be a challenge for that. That won't.
I feel like the lowest like 640. But
Jeff, let's follow up afterwards. I actually think I know this application. So
cool. Great questions so far, guys. Keep them coming. We're gonna just keep talking about hot plate welding for a minute, and then we'll go to laser welding because we're already in the vein. So let's stay here. Some of the main benefits of hot plate welding is you get very strong welds. It's a leak-proof process. So if you have a joint that is a full perimeter, then you can expect to get a leak-proof weld, a hermetic seal. And then there's no particulate. It's not vibratory, so you don't get all these shavings, plastic dust everywhere that you get with some others. I want to show why you can expect really strong welds from hot plate welding. And the main reason is it normalizes the weld joint. It's the only technology that does this. So if we zoom in on the weld and you look close, plastic parts be plasticking.
Is that what Nick said earlier?
It's going to stay with me for a while.
It's not flat. And when I say flat, I mean it's not to CAD. It doesn't mean that we can't have curved parts and contoured plastic parts when you're hot plate welding. But for the sake of easier discussion, say your part's supposed to be flat. It's not. There's never been a flat plastic part, and there's just going to be some amount of warp. And so what happens in hot plate welding is the tooling comes and melts that plastic part flat. And when it retracts, now you have two plastic parts that are both flat. They're parallel to each other. So you have two even surfaces. And so when those two parallel surfaces are pressed together, you've got consistent pressure across the entire part. You're getting the right amount of force into your whole weld profile, which makes for a strong leak-proof weld.
I'll also say that it also does the best job at internal stresses. Vibration welding is a really effective weld process, but Jason just sort of talked about normalizing the weld plane. It doesn't do that. It melts the heck out of parts, which is really good about that technology, but it also will force non-flat parts together, therefore inducing a ton of internal stresses.
Yeah.
So it can be really effective with stickier plastics that cannot be hot plate welded, but I would say hot plate really not only gets your part back to CAD, quote unquote, it also allows for very, very low stresses inside the part itself.
Not to mention the precision. that the parts are melted to? What's the tolerance?
1 thou.
1,000 of an inch.
Pretty precise.
Yep.
I think so.
So if hot plate welding is so great, then why wouldn't you use it all the time?
That's a really good question.
That's a good question.
The material is probably one of the biggest indicators on when you would or wouldn't use hot plate welding. Nick had mentioned earlier that we'll do a ton of polypropylene with hot plate. You saw a video of PCABS, sometimes in the lenses, but they can get a little bit stringy on the heated tool. HDPE, LDPE, we'll see those a lot as well. The biggest indicator that you do not want to approach hot plate welding is if you're doing a nylon or a PBT. Those two materials, when they touch hot things, get really sticky, stringy, nasty. And let me tell you, you do not want to be cleaning that off your heated tool or smelling it as it sits on your heated tool.
Yeah.
I'd say the next big thing would be fillers. Just being conscious of your fillers. Glass is going to be abrasive, so that is something to consider when it comes to tool wear. You wouldn't want a Teflon coated tool and then glass content.
Yeah. And if you've cooked with a Teflon pan, you know that they start to flake off. It's the same thing with it's probably a better Teflon than what we're using than what is in a pan, but it's not immune to wear.
Mm-hmm. So I'd say the biggest indicator would be the nylon and the PVT with fillers is kind of a close thing to follow, just as a point of consideration.
Yeah. Hot plate welding equipment comes in several different form factors. We make a lot of different things here at Extol. The thing on the far left, a small modular hot plate welder. Think something that looks like a benchtop unit with a single column, and it works really well if you're welding really small parts to larger assemblies. Mm-hmm. Think like small ports or brackets being welded to something larger. That a small modular hot plate welder is really, really cost effective for that. We have a rapid conductor hot plate welder here at Extol, and then we've recently released our new Titan series welding platform that's capable of hot plate welding and IR welding, and we'll get into that a little bit later. And then really large form factor welders. So the one on the far right there is made to weld pallets. We've done large dunnage and other types of like large grades and stuff like containers. Thank you. Like things that have like a 4x6 foot footprint. Those can be hot plate welded too. It's just the equipment's going to have to be a lot larger, and we've got experience in all of that. Mm-hmm. That is hot plate welding in a nutshell. Please keep the questions coming. We're going to jump into laser welding because there was so many people that when they signed up said, I want to know about laser welding. So who wants it?
I'll take it.
Okay.
I got it.
It's a little faster than you, Catherine. Sorry.
All right. So
an arm wrestle.
That's right. So laser plastic welding has been around for a long time. It's a fairly straightforward process and concept. The nuances we'll talk about in just a moment. What you see in the images on your screen are through transmission. Do we have, I think, talk about 2 micron and direct laser in this?
Yeah,
actually.
But we're going to focus on through.
Yep. Through transmission is essentially where the laser is applied through a top layer and into a bottom absorptive layer. You have to apply pressure. You've got to get the laser focused correctly and make sure that you're hitting the path. And then it's a cooling process. So very, very straightforward in concept. The key elements, we say the 3 key elements for laser plastic welding are intimate contact. It's crucial that you have the parts in contact with one another. And the reason for that is the heat transfer that happens from the lower to the upper is really important because that part's absorbing that IR energy. And in order to have a good bond, anyway, you need contact. But on top of that, you're actually transferring heat into the upper as well. So intimate contact, there's a lot of tooling tricks that are required to do that. The second key element is IR transmissivity and absorptivity. Both of those things for through transmission need to be properly engineered, and you've got to make sure that you have good transmissivity in the upper parts and absorptivity, that the parts are absorbing the IR energy really well. And then you got to have compatible materials. You don't have to have the same materials. We talked lenses in this application, in this webinar, and PMMA to PCABS is very common, and that works great with laser plastic welding as well.
Yep.
So you have to have these three things in order to have a good welding application.
A question that I get asked a lot, Nick, I'm curious your thoughts. I'm putting you on the spot.
Yeah, let's have it. Come
on. Flatness tolerance. I get asked a lot,
All the time.
specifically because of the intimate contact being a key factor for laser welding. What sort of tolerancing do we?
I would say it depends on the size of the parts, and it depends on how much force and pressure we can apply. So, for instance, the video that you're about to see on the left, we'll play it in just a moment. I think those parts were probably plus or minus 20 thou, 30 thou. Like, you could sort of lay the parts on a nest or on a table in its natural state, and you could see a pretty substantial gap, maybe a 30 thou gap on them. But we were applying, in this particular application, about 2,000 pounds of force to two parts. That flatness tolerance is not an issue when you're applying that much force. So the answer is it depends on how much pressure we can apply to the parts. And in a natural state, we expect there to be some warp. So those two parts were planar. They were two-dimensional shapes and were designed to be flat. We have done some circular parts where we do like a radial weld, and those dimensional tolerances should really be tighter. 0.2 millimeters, 10,000, somewhere around there. But I've seen us get, in the glass filled nylon space, I've seen us deal with parts that were like 3 millimeters out of flat. Yeah. So I probably should have led with that. Yeah.
And we've
Can
done
you
it
edit that?
successfully.
Can you edit that out? Yeah, we've done it successfully. So how much? Yeah, that's right. And so the answer to the question is, how much force can we apply? We make sure that we've got accommodations for that in our nesting. So we might need to adjust the nest with shims. Some companies don't love that, but you're dealing with plastic, and so if your mold, if you're running a 6-cavity mold application where cavity 2 just always is a little bit lower on that, that one corner, we have to make sure we can accommodate for that variation across multiple parts.
What's the worst? What's the bad that happens if you put a part that looks like a potato chip in the laser welder?
Probably what I mentioned earlier with the internal stresses. We're gonna make it flat, really aggressively if we need to. So I would say, can we do that in a way that doesn't adversely affect the part? Mm-hmm. And then what I'll also say is, if you don't have good contact, we can see burning. That's very rare. I've only seen that out of, I don't know, hundreds of applications, maybe 3 or 4 times. So I would say we can typically accommodate pretty wide tolerances. Precisely how much we'd have to get into. Great question. I'm glad to hear that that's coming.
And you're talking about warp. Would you agree that a bigger issue would be like if you have a mark on your weld profile, like if you have an ejector pin that's pushing on your weld rib and it's making a 40 thou dent in the ply, that's much harder. Like we usually can't press that out. I
actually have seen us do that.
Really?
I have seen us press out like a knit line or a seam from a mold.
Not recommended.
Not recommended, but not all recommendations get followed. So we did have that on a production application and pressed it out.
Yeah. Okay.
But we had to apply we've done presses. Here's what I would say. Typically, most laser welding companies don't apply the kind of force that we typically apply. I've seen us be successful in applications where others weren't because we're using hydraulic pressure, like 6,000 pounds of force. Now that was a very wide weld rib, but we will fine tune that pressure. That's really, really critical.
Cool.
Yep.
All right, let's check this video out. Hey, look, it's Nick. I'm gonna mute this one, okay, because it's just too distracting.
Yeah. Is the video coming? Can we get some feedback maybe on how the video is coming through? It's pretty choppy for me as I watch here.
Wow. Yeah.
Is it smooth for folks?
Sucks to be you guys. I can see it great.
Well, we got.
Jeff says it's great.
Jeff says it's great.
Okay, good.
You got a good question from Max.
Okay. welded. Now it's being laser marked. 2 different processes. Okay, pretty straightforward. Now, to answer Max's question, let's show this right here.
Yeah.
Okay.
So there are different types of laser plastic welding. Transmissive 1 micron is by far the most common that we see. We have done some direct laser to the right, where essentially you are shooting both parts, getting them really, really hot, and pressing them together. When that happens, you generate a pretty substantial amount of smoke. For transmissive and clear to clear 2 micron, Max, in your question, if there's an air gap, if that plastic's allowed to absorb that IR energy, it usually will oxidate. Whereas if you have good intimate contact, there's no oxygen getting to the surface. And so that energy that's getting poured into that surface is actually conducting up into the part. In rare cases, we have seen, and I'm talking if the laser's on for 20, 30 seconds, we have seen blistering. But that's rare, and we can typically process that out if you have proper transmissive properties. So to your question, laser is going through air. Like it's, we get heat from the sun going through a vacuum even. So infrared energy can go through air. The reason we say we need intimate contact, 1, is to make sure both parts get hot, and 2, you can get excessive smoke if you don't have that intimate contact. On the direct laser applications we've done in production, we had just used simply a smoke management system. Very simple, very straightforward. I think we have a video. Yeah. I don't know. I'm putting Jason on the spot. This is a direct laser application.
So you'll notice the smoke. But here, the intimate contact, there's no intimate contact because we're applying the energy directly to both sides of the assembly and then bringing them together.
Right.
So you get the smoke because there's nothing to keep it from oxidizing.
Right.
And you still get good weld because we're applying the pressure afterwards. With a normal through transmission weld, you need it mainly to make sure you get heat into your plastic parts.
And we have done 2 micron with direct laser plastic welding, and that smoke can be quite a bit lower. It sort of absorbs slower, gets you a deeper heat affected zone.
Yeah.
But it's essentially what we're doing there is just shifting it to IR welding. Laser is infrared energy, these wavelengths, but we have 2 other methodologies for infrared welding, which I think we'll talk about in just a moment.
Yeah.
Great question, Max.
Another good question. Are direct laser welds as strong as the transmissive?
Ooh, Elizabeth's very, no, not so much, actually. We can get 80%, 90% laser parent material strength through transmission. Direct laser, you do see some reduction. So we typically will recommend, if your wall thickness, I'm just making up numbers, is 2 millimeters thick, we typically will recommend like a 6 millimeter or 5 millimeter weld thickness. So you can still get the strength. You're just having to weld more surface area to do that.
Yeah.
Max.
Okay, let's get through the couple different types. Of laser plastic welding, because we've been showing quasi-simultaneous.
That's right.
But there's others.
Yeah, quasi-simultaneous is many passes really fast, and you're for true transmission, you're simultaneously displacing material. You'll notice if you watch that video, even if it's not choppy for you, that's actually a circular beam, but it sort of shows as a line, and that's because the video is just not at the rate of the camera can't keep up with the scanner.
30 frames per second.
Yeah, and I think this application was like 3,000, 4,000 millimeters per second. So that is quasi-simultaneous laser plastic welding. Again, that laser's kind of jumping around, but what it's actually doing is tracing that with a 6 millimeter beam spot or 5 millimeter beam spot. So you got quasi-simultaneous. You have contour welding. Contour welding is one continuous pass along the laser. This can be effective for smaller parts. Larger parts can get, you can build some stresses into it, and we've seen that it can be effective most of the time, but sometimes you need quasi-simultaneous. Masking is just another tool. We don't use it much. It's a tool in the toolbox for really, really small welds. You're literally just masking the part off on the clamping tool. And then simultaneous, I mentioned earlier, Catherine asked about what's alternatives to vibration welding. And we see this. We have a partnership with a company that does this. Lasers are individually distributed over that weld joint using fiber optics and waveguides. And you could do really complex shapes with this. The downside of that is cost. They can be quite costly. Yeah.
You mentioned two kind of tipping points between quasi and simultaneous.
Mm-hmm.
Is there any other that I feel like those are the two most commonly discussed?
Yeah,
laser
I would say so.
So are there any other, kind of like how we talked about hot plate, how there are materials that would be kind of a yay, nay in either direction? What about quasi versus simultaneous?
I would say, the same principles apply for absorptive and transmissive parts. Direct laser, you just need absorptive, right? So I would say not from a material standpoint. I will say a big benefit to quasi-simultaneous, and I think people think laser and they think super expensive. That's just not necessarily the case with quasi-simultaneous laser welding. The tooling cost is actually quite low. In some cases, less cost on vibration or ultrasonic. And so you might have a little more capital cost, but your tooling cost might be lower. So I just think that's noteworthy. It's not necessarily your question, but yeah.
So benefits of laser welding, you get a really clean, precise weld that happens pretty quick. Even with quasi-simultaneous, you can get some pretty fast cycle times.
Mm-hmm. Yep.
We're going to jump ahead. The other topics that we're most interested in, we've talked about laser, we've talked about hot plate. We're going to talk about ultrasonic and vibration. And I want to quickly dispel. So a long time ago, we posted a blog post that explains the difference between these two, because it's one of the most, it's easily confused because both are vibrating, and only one of them is ultrasonic frequencies. So when we talk about vibration welding, we're saying linear vibration side to side, like the graphic shows. When we say ultrasonic welding, we're talking about vibrations up and down, sort of like a jackhammer, but much smaller. They have very different frequencies. So frequency is, one vibration would be forward and back. That's a frequency. That's one time. And so a vibration weld does that 120 times a second. Some vibration machines go 240 hertz or 240 times per second. Ultrasonic welding, it's called ultrasonic because it's above the human hearing range. The only exception is 15 kilohertz, but we're splitting hairs.
Good enough.
20,000 times a second, that's 20 kilohertz. I mean, it's like orders of magnitude higher frequency, right? This is happening very, very fast. And this isn't even all of the ultrasonic frequencies that you can get. They're like 20, 30, 35, 40. I don't know. Is there a 45? Somebody's probably doing 45 kilohertz. So. Just like crazy fast frequency. The other side of this is amplitude. So the amplitude is the distance that one vibration is moving. In linear vibration welding, that movement is anywhere from 0.4 millimeters to 4 millimeters. It sounds small, but you think about it, you have to have that much room in your weld joint for the parts to slide amongst each other. Ultrasonic is like teensy tiny. Look, it's 0.025 millimeters to 0.125 millimeters.
Portions of a human hair.
Yes. Very,
very small portion.
Tiny. So like when an ultrasonic horn is vibrating, you can't see anything happening. You can feel it, but you can't see it. So
I was just going to say, Jason mentioned that you can't hear it. If you have run an ultrasonic system, it can have a pretty awful screeching sound.
Yeah.
And that is essentially a stationary piece of plastic meeting this horn that's putting a substantial amount of energy into the part. So, just to sort of,
and there's resonant frequencies that you do hear.
Resonance that
are lower.
Yeah. It can be loud, but the horn itself, if you're just running it, and not in contact, is silent.
Yep. Quick question before we keep going on.
Oh yeah. This is radio weld. So this would be for laser plastic welding.
Yep.
We typically will rotate the laser around the part, and we do that in using a mirror to bounce the laser to the weld rib. We have helped customers ensure you have proper contact, so we can make design recommendations for that. What level of fixturing is generally required. I would say it depends on the interference. We typically like to see a little bit of part interference. So you think in terms of like a press fit. So if you have that good press fit, like we had a catheter application that in the medical space that had inherent interference fit, essentially. Didn't need any pressure. We had a part that was actually had a fairly, I don't remember the numbers, but had some variation. And so we had a taper on that weld rib, and we did have to apply like 400, 500 pounds on that part. That was, I think, a fitting. So I would say we can help you with your specific application because it really depends. Are you doing a small tube? Are you doing a 6-inch diameter? We typically don't rotate the part. We just let the laser do the work because the light's easier to move than the part itself. But we can rotate parts if you really want to see that.
Back to vibration welding. I'm going to quickly show through my fancy animations here how a vibration machine vibrates. You have a large metal spring, and I couldn't get the thing to like skew, but it would actually be like flexing. The bottom of that spring, imagine that it's moving with that metal plate that's sliding back and forth. And there's big electromagnets on either side of this thing that are pulling the upper tooling left and right, back and forth very quickly. So that's how vibration vibrates. Here's what the process looks like. First, you come and you clamp those parts together. You continue your clamp force as you vibrate, allowing them to displace into each other, and then you stop your vibration, let them cool, and then your part is done. There is a variation to this called hybrid vibration welding. Maybe you've heard of it. And that introduces an IR preheat. And so you bring these parts into an IR tool that it softens the weld ribs of both components before it does the vibration process. And that allows it to reduce some of the particulate that you might see. It can create stronger welds. There's some benefits to that. It does make the process longer, and it does make the equipment more expensive, but there's some applications that really benefit from a hybrid vibe.
Yep.
Now we're jumping to ultrasonics. So how does an ultrasonic horn vibrate? And this is the crazy part. If you've never seen this before, this might blow your mind. So that what we call it a horn, it's literally the metal is expanding and contracting. So on the top side of the horn, it's going up and down. On the bottom side, it's going up and down. And that vibration, now this is obviously exaggerated because remember, we're splitting hairs, human hairs amount of amplitude. And those vibrations cause the molecules in the plastic to have friction with each other and heat up. And it's wicked fast. Like you turn this thing on and it's like right now you're melting plastic. The ultrasonic process, you load your parts, the ultrasonic horn comes down and you vibrate that horn. Usually ultrasonic performs best when you have a sharp initial point of contact. That's why there's a little triangle. You call them energy directors. You probably heard that term. And those energy directors allow that initial point, that melt to start really quickly. And then you melt it down with the ultrasonic energy. You turn the horn off and then just press on it, using it to press your parts together and get those bonds to happen.
There's a question very early on talking about strength.
Yes.
Jason, what are your thoughts on ultrasonic and vibration welding strength compared to parent?
Ultrasonic welds are typically smaller than vibration welds. And part size and weld rib width. Ultrasonic ribs are usually quite, comparatively so, quite large. And for that reason, I would say vibration welds are usually stronger. As far as percentage of parent material, I honestly don't know. Vibration, I can answer this. Vibration welding is often used to weld big, if you've ever seen a plastic engine manifold, think, big glass-filled nylon parts, and there's multiple layers to that. Those are often vibration welded, and those parts are going into an engine hot, and it's strong enough and leak-proof enough for that application.
I do think that in that particular application, because we've seen a number of those joints over the years, they typically will cheat by having a very large weld rib.
Yeah.
to try to get that strength.
Yeah.
So inherently, you just need a lot of strength because of all the stress. I've seen parts literally almost a quarter of an inch out of tolerance be successfully vibe welded. A lot of stress, a lot of inherent stress in it. But I think Jason's right. And ultrasonic welding, probably many folks on this webinar know, are typically smaller parts. The horn really can have size limitations to it. So the other thing about ultrasonic welding that's kind of noteworthy that you can kind of see the horn coming in contact, you can't really have a large distance between that weld rib area and where the horn contacts. That's called far field welding. If you've heard that term, it essentially just means that the weld field is really far from the horn itself. We've had laser welding ultrasonic applications switch to laser welding because that design just had constraints or was designed incorrectly, and we're already, the mold tools were already ready to go. So just another thing to keep in mind with ultrasonic welding, you have to be mindful of that weld rib location.
One other thing that I have heard come up a lot recently is the topic of annealing.
Oh.
Mm-hmm.
Specifically as it pertains to vibratory processes.
Yep.
Nick, what are your thoughts?
I mean, a lot of companies will spec it. They'll specify it. Like their customer will specify that because there's just no way around that internal stress.
Yeah. You don't allow those bonds to the molecules to relax.
Yeah. It's whip. It's additional equipment. You don't need that with laser welding. You don't need that with hot plate welding. I don't know of any ultrasonic applications that require that, but I guess in theory, maybe. But Vibe is definitely
smaller lenses.
Yeah, maybe.
What distance is considered far field? I have this answer. Hold on. Wait for it.
Jason on the fly.
I just wrote this down.
On the fly is tapping into his OneNote. You guys would be so impressed with this.
Quarter inch.
That's across
greater than.
If it's thicker than a quarter inch, it's generally considered far field. If it's smaller than that, in millimeters, crap. I don't know.
About 6 millimeters. About 5 to 6 millimeters.
I'm an American.
We should show IR welding just really quick.
Okay, let's talk about IR. We're tight on time.
Yeah,
we'll
you
go
guys
over
have been very gracious and this is good. Thank you. We just want to showcase and sort of talk about IR welding. Okay, so if you can't vibe weld it because your parts are too sensitive, hot plate the plastics, it's going to be sticky. You might need, laser welding. You really can't get a good transmissive upper, so you might need to use IR welding. We have two methodologies we use for emitters, but just the process in general, you've got an IR source, two plastic parts come into close proximity to that part. Open time, you get that IR source out of the way, and then you press it just like the hot plate welding process. Instead of touching it, you sort of hover.
Yeah.
There are 4 kinds of emitters for IR welding. Straight quartz emitters, if your parts are flat. Those we like one key supplier for these kinds of emitters. It's not a commercial, so I'm not going to get into that. Custom quartz emitters. This is a custom shape. Can be effective, but can also be long lead time. We have a technology called InfraGuide, and so I think we'll show an image of that really quickly. But those are very cost effective, very small. Think finite IR sources where you can actually turn things up and down on that. How hot? Real hot, Jeff. Real hot. It's actually a great question that actually kind of affects people's paradigm, because you think in terms of how hot is that heat plate? My control parameter is heat.
Right.
With infrared energy, it's irrelevant. It's how hot the part is. So there are some process monitoring that we'll do with IR point sensors, which are pretty cost effective, or thermal cameras. We've got a really key supplier that does some process monitoring with that. So the process parameters really are depth, time, and power level.
Yeah.
And so we have different power level settings that will apply to all of these, all 3 of those methodologies. And then seal parameters are the same as hot plate welding. So great question on temperature. We say as much as it takes in power to make sure you get the heat affected zone that you want.
Yeah, because the filament of the bulb is thousands of degrees. but you're not touching.
I love AI. We got a note taker, follow-up action items.
Nice.
It's fantastic.
The last IR source is laser, because believe it or not, laser is in the IR spectrum. And when we do direct laser welding, that's really a form of IR welding. We have two separate parts. We're applying the energy and then we're bringing them together.
Yep.
There's two different ways to control infrared energy, two main ways, I would say. Masked energy, where you have those the custom quartz emitters that we saw, and the straight emitters. If you want to keep that IR energy off of other areas of the part that you're not welding, you'll need to mask the tool. You'll have to have a metal plate in there that blocks the IR energy from getting there. And as you can see from the graphic, it does an okay job of keeping that IR energy off. Flip side is what we use in InfraGuide. That's focused energy. We're not simply just masking it. We're actually taking it and we're corralling it. And we have engineered surfaces that are designed to focus it onto the weld rib, which is improving of efficiency. It makes things faster. It uses less power. And it makes it so that there's like no stray energy getting where it doesn't belong. Then there's something that's kind of in the middle between those two, right?
That's right.
And what you can see here in this image, I'm going to play it in just a second, but I want you to look really close. Actually, I'm going to zoom in. Can I zoom in? Give me the zoom. Look closely right there, kind of in the middle of the screen. Let's see if it'll let me do the laser point at the same time. No, silly PowerPoint. Okay, right here. We're looking right there. This piece is the mask, but it's what we like to call a
focus mask.
Focus mask. See the angle slots here? That's for a reason. So that takes the energy and actually partially focuses it to reduce energy power consumption, improve efficiency, but it's more simple than InfraGuide, which makes it suitable for large parts with lots of internal weld ribs.
Yep.
And so that's what was being used here. You can see all the IR emitters turning on, and then those partially focused masks are used to get the energy where it belongs. And then the other benefit here, this is two very like thin flat parts that were like potato chip.
Yeah.
And we can actually use the mask to clamp and make those parts a little flatter while we're heating.
Yep. InfraGuide is probably the most common that we see. And our Titan is a standard platform to run those in.
Yep.
Again, same process, but we've been using these kind of emitters for 25 years. This is a complex shape. Yep. So we had multiple angles. That's actually not even the most aggressive angle we can do. And you'll notice the pulsing. That, the question about temperature is a great one, because we had to use power to essentially match the rate of conduction in the parts with the surface absorption. So we can do that in a variety of different ways: smaller ports, smaller parts, fittings, and then this was an air induction system kind of application.
A quick plug for the Titan series welder. We mentioned that it can do hot plate, it can do IR, it can do both InfraGuide IR, which is unique to Extol, and then there's the quartz IR, which is those straight emitters or those custom bulbs. The Titan series welder is low cost. It's flexible because you can have all these different welding technologies in it. It's got a small footprint. If you've ever purchased a rapid conductor from Extol, we actually shrunk the size of this machine by 8 inches. So it's a smaller footprint, and it's automation ready. So this can be configured in a couple different ways. We have the standard configuration. We can have it so that it's built where the front is basically missing, and you can integrate it into an automated line. It's a modular design, which makes it much easier for if you wanted a pass-through design. We can just remove that lower press platen and replace it with one that's built for a conveyor to come in. You can add robots to it. We can customize it kind of any number of ways with like rear tool load, add a robot to it, lots of different options. So that's the Titan series welder. You can get yours today at Extol. Felt like I was making a sales pitch. We got another question?
Do you control bolt temp when starting the next weld? Control or monitor? We do not. Typically, there might be a 3 to 5 cycle warm up, and then it runs consistent welds. We do monitor depth, seal depth, and seal force.
Yeah.
If a company wants us to monitor temperature, we don't do it of the bulb. We do it of the part itself.
Yeah.
Because that's all that matters.
Yeah.
That bulb, that emitter is burning at around 2,000
Kelvin?
I think K. Yeah. I think. Or not burning, but that's the color temperature of it.
Yeah.
Life cycle emitters. For infraguide, roughly 1,500 to 2,000 hours is what we typically will share.
Yeah.
Quartz is kind of all over the place. There are companies out there that use like really low cost ones that are 300 or 400 hours. We typically do not. I think it's 5,000 hours of the emitters that we like.
Yeah.
Custom ones might be lower than that, but
yeah. We also monitor the current going to each bulb. So if a bulb burns out, the machine will know, and it'll know which bulb, and then you can replace it. Some customers replace just the bulbs as they burn out. Some customers have a PM schedule, and they know how much on time, and then they say, okay, let's replace them all.
Yep.
Just so that we don't have to keep stopping production.
Jason, I think we're out of time.
Oh my, we're out of time. Okay,
Yep.
so thank you everybody for joining. We can stick around if you guys want to ask a bunch of questions. Otherwise, we can wrap this thing up. But I want to hold on before everybody leaves. You don't have to remember all of the technologies that you saw here today. We have a plastic welding decision matrix available for you. This decision matrix highlights a bunch of the different welding technologies and then compares those with the different criteria that your application might have. Does it need a hermetic seal? Does it need high burst strength? Those types of things. And then you can use this to say, all right, which technologies should I consider? It's not a end-all guide. It's a general initial guideline to get you thinking about the technologies that you might have at your disposal. When it's time to look at your application more specifically, that's what we can help you with. We partner with companies to look at your application and look at all of the things that make your company unique and make the application unique, and we come up with the best solution to help you with that.
Jeff just asked about non-contact hot plate. We have done that, Jeff. I would highly recommend you get your parts closer than 50 millimeters to the heat plate and be over 900 or 950 Fahrenheit. We'd like 1,000.
50 millimeters?
What did I say?
You said 50 millimeters.
50 thou.
50,000.
Which
Thank you, Catherine.
that is closer than 50 millimeters.
It is.
Oh, yeah.
I was not wrong. Real close.
You need to be a lot closer than that.
We've done applications where we've had 1,200 Fahrenheit. You really got to get that temperature way up there.
Mhm.
And not everyone's welders can do that.
Yep.
Great question. Man, that's a deep dive. Max asked about
wants to ask a question about bulb control.
let's go. Let's have it, Max.
Let's hear it, Max. You can get help from us, but this is how you get help from us. You can either scan that code. That'll take you to a quick form on our website where you can submit it, and we'll get back with you. Or you can just send an email to sales@extol.com. That'll go to one of us, and we'll be able to answer it for you. There's real people on the other side of that inbox.
I'm the real people.
It's her.
It's me.
But I can check it too. It's a shared mailbox. So we'll discuss your project and work together to come up with a great solution. We only sell great solutions. If we think it's going to be a bad application, we're like, don't do it.
Yeah. We say, let's find another solution.
Yeah.
All right. So it looks like Max is asking from past project on our welding, I had to control the bulb temperature and the mask temperature before the next weld, since depending on the time, bulb set start temperature differs.
Oh, yeah. The ramp up time of the...
Yeah. So we have seen that kind of thing with the quartz emitter space, but our infraguide is incredibly intense in energy and actually can have a really wide process window. I've seen us do white nylon, which we needed to be really careful we weren't going to burn it or brown it. And we had about 20-ish, 23, 24 seconds of melt with like a 5-second process window. So I think maybe the answer to your question is, how wide is the process window? If we determine that, and we typically would vet this out in our applications lab, that's really critical and you've got maybe some sensitive components or the material needs, itself has a tighter process window. I would say we would recommend a part specific temp sensor. Again, really the IR emission is those bulbs are not really controlled. They're pulling a certain current and they're designed for 100 watts. Those small bulbs are 100 watts each. Monitoring the temperature is not terribly accurate for what the part perceives. What I'll say is the temperature, honestly, is kind of irrelevant because it's how much energy gets into the part. And so it's absorptive properties and the thermal properties, how much heat is being sort of conducted and dispersed through the part. That all is way more important than, hey, what's the temperature of this emitter that we're using?
I have seen, to try to minimize the ramp up time.
Oh, yeah.
I have seen IR welders that the quartz bulb never truly extinguishes. It might after 15 minutes, but like part to part, it stays partially lit or fully lit, which I don't know that I'd want to do that, but like it'll dim, but you can see it glowing while it's in the retracted state. And then when it comes forward to weld, it, fully illuminates, and that can reduce if you were to sit there totally cold and then start the next cycle, it's going to take maybe a little bit longer to get to that full temperature of the filament, and then could impact the process. I don't know if yours does that or not, but that's just another possible solution.
Your application with quartz is absolutely going to be a little trickier than infrared. Now, what we didn't say about infrared, and we've lost about half the audience, is the design might be a little more constrained with infrared. So we're optically engineering those, as Jason said, those surfaces, which gives really intense energy and really focused energy. But you might lack a little flexibility on, really small parts or parts that have really tight constraints. Yeah, this is a tool that we made, and that was flat. We've done non-flat tools as well, but making sure that you can give consistent focused energy is where we've put our efforts. And Jason's right. We've seen quartz applications where the emitters just stay on, and it's a power hog. I mean, it uses a lot of energy and creates a lot of heat. So it sounds like you're kind of in your application with the tool that you purchased, doing it probably the way that we would suggest. If you switch to infraguide, I don't think you need that. I know that you wouldn't need that. We have deployed dozens of these tools, and temperature is just really not. We look at the weld quality, the seal, the force, and then we're just running sort of open loop on the temperature, because temperature doesn't matter very much.
Cool.
Good.
Thanks for joining. I really appreciate all of the great questions that you guys asked. And you'll be seeing a email come through shortly, within the next few hours, hopefully, that has the recording, slides, the plastic welding decision matrix. And please reply to that if you have any further questions or you want some help on your project. Thanks everybody for joining. Have a great rest of your day.